I did my presentation on nitride nanoparticles. So I do want to start off with just a brief introduction about some nanotechnology. So nanotechnology does deal with the science of very small things that can make a huge impact on society. And the image on the lower right is actually a graphene sheet that's rolled up into a carbon nanotube. And so these nanotechnology has been around for several years, and nanotechnology does incorporate all aspects of chemistry with nanoscale dimensions, so objects can be made, assembled, and understood. And you can see on the top right that these nanotubes can be very complicated, and there can be quite a few layers on them. So nanomaterials can have very interesting properties which may act differently when in their macroscopic form. So nanotechnology is still a very much a growing field of chemical and material sciences and new remedies and machines and devices. So this image on your right, it is actually very interesting because it's the kerosene dipeptide in addition to a carbon nanotube, and when placed into some sort of electric current, the kerosene dipeptide can actually go within the carbon nanotube. And this is actually a mechanism that can be used to transport medications because kerosene dipeptide is actually a medication. So this is one of the very large opportunities of nanotechnology, just because it is a very extensive field, and if it can be used to transport medications, then it can be very beneficial in the field of medicine. So defining nanotechnology just a little bit more, the word nano comes from the Greek word dwarf, and nanotechnology is the study of very small objects, and so the nanoscale does range from about 1 to 100 nanometers. And nanotechnology is slightly larger than an atom, so it's about tenfold larger than an atom. And this little scale on your right kind of puts it into a little bit more perspective. So on the very far right, we can see a watermelon is about 10 meters across, and then we get to a quarter, down to a pen, down to a hair, red blood cell virus, and all the way down. We can see toward more the microscopic, a gold nanoparticle, carbon nanotube, a benzene molecule, and then finally down to a water molecule that's about 10 to the negative 10 meters. So as you can see, these objects can get very small very quickly. So a little bit more, when working with larger nanoparticles around 100 nanometers, this is known as the realm of microtechnology. And microtechnology is often used in computer chips. So this image on your right is a piece of hardware from a computer, and you can see just how relatively small it is compared to a penny, and most likely how fragile it can be. So working with these materials can often be quite difficult if not handled properly, so it is very important to have the right techniques and right technology to be working with everything. And nanoparticles can get as small as DNA molecules and as large as some size of a computer chip, like what we saw on the previous slide. Chemistry, biology, and physics is also a very important knowledge to have when studying these nanoparticles. So this image on your right is, of course, a double-stranded DNA molecule, and so it can get as small as these DNA molecules, usually not any smaller, but it can get very complicated as well. And so just providing a little bit of a history of nanotechnology, first of all, in 1959, a physicist named Richard P. Feynman gave a lecture about being able to manipulate atoms one by one. And hypothetically, Feynman compared atoms to machines and what would happen if machines were to get smaller and smaller until they were on the molecular level. So these machines he was referring to are these nanoparticles. At the time, he was just kind of hypothetically talking about them as if you know, they could be something in the future. As we'll see, some of these scientists kind of ran with this idea and started to become more interested in this type of technology that could be developed. And so we see back in 1974, the term nanotechnology was first used by Professor Norio Taniguchi, where he discussed the materials within the semiconductor industry. So this made scientists consider the possibilities of what can be done on a nanoscale. And really, as time goes on, you know, the years pass, and we can see that as technology becomes more advanced and everything becomes more possible, it becomes very easier to develop this technology. Back when, if we go back to the previous slide, in 1959, when Feynman initially talked about these nanoparticles, the technology may have not been there to produce these. So as time goes on, of course, this technology becomes more readily available. And in 1989, two scientists by the name of Gerd Binning and Heinrich Rohrer, if I said those correctly, created a scanning tunneling microscope which were able to neatly arrange xenon atoms. And then because of their work, they did receive the Nobel Prize for their invention in 1986. So the images on your right are actually pretty interesting. The bottom right is actually an image of the tunneling microscope. I'm not sure if that's the one they actually used or just kind of a more modern version of it, but I'm assuming it's very similar. The image on the top, it is an image of what the microscope would be able to produce. So I'm not entirely sure what that would be, but I'm assuming it's some sort of nanoparticle. But you can see how very well developed those images are, and you can actually see everything on the outside. But that's kind of one downside of it, is you can only see things on the outside rather than seeing a view of what's going on the inside, which is where most of the chemistry takes place. And then continuing, in 1985, a group of researchers discovered fullerenes, which are soccer ball-shaped shell structures comprised of 60 carbon atoms. Commonly known as buckyball, after the scientist who discovered it, Buckminster Fuller, if I said that right. This discovery led to researchers consider these fullerenes as cavities that could carry drugs throughout the body, kind of like what we discussed earlier. This is currently a huge field of research, and you can see on the right is all sorts of different fullerenes. So you can see on the top left there's carbon 60, which is the buckyball shape, and then they kind of increase from there. You can see that carbon 70 kind of has a more of a pentagon shape, while carbon 76 more of a hexagonal shape, and then kind of these geometric shapes become more and more complicated as more carbon atoms become into place. So it is very important for drug synthesis and drug traveling within organic people or animals. So this is a huge field of research as of right now. So just a little bit more about nitrides. So nitrides are compounds that contain nitrogen with a formal oxidation state of -3. They do typically have high lattice energies, and nitride compounds have large band gaps, which are useful when creating insulators or wide band gap semiconductors. So a few examples of these nitrides are boron nitride, silicon nitride, and gallium nitride. And gallium nitride emits blue light within LEDs, which is one of the many applications that come with it. And those three examples are going to be the focus of this discussion, the boron, silicon, and gallium nitrides. And the image on your right is I believe it is carbon and nitrogen. So they do come in these hexagonal shapes. So you'll see kind of a trend with all of these types of nitrides and their nanoparticles. They all have these kind of similar properties, but we'll discuss it more as we go. Properties of nanoparticles. Before we get into some more specifics in regards to the three that we're going to talk about in this talk, I just wanted to discuss some generalized ones. So there are four, but there are more, of course. The first one is interfacial layer. So when we talk about the interfacial layer, we talk about when dispersed in a medium of different composition, so with different particles floating around in some sort of solution possibly. The interfacial layer can change its chemical and physical properties due to the nanoparticle. And then there's also another property called a solvent of affinity. So what that means is a suspension of nanoparticles that are possible. Well, suspensions of nanoparticles are possible since the interactions with the particle surface is strong enough to overcome diversity differences, and this results in a material that sinks or floats. So say like you put a nanoparticle in some sort of solution, or it's already in some sort of solution, and if you were to add some other interaction, say it's sodium chloride for example, that sort of interaction with the nanoparticle can result in a material, kind of like a crystallization, that can cause the particles to sink or float. There's coatings as well. So when discussing coatings, they are nanoparticles could receive coatings or other particles of the surrounding material. So kind of going back on the sodium chloride, for example, using this image on the right as an example, so for say like a sample of sodium chloride can bond to one of these long branches that extend from the nanoparticle. This can cause, probably wouldn't likely cause major differences within the nanoparticle, but it's just another consideration when discussing them. And then there's also a diffusion across a surface. So the high surface area of nanoparticles do allow heat, molecules, and ions to easily diffuse across the particles, and sometimes it can be very high rates. So very much like a cellular membrane, these nanoparticles have these membranes on the outside of them that can diffuse smaller particles, energy in the form of heat, and of course ions across them. Then they can possibly do some chemical reaction on the inside depending on the particle that gets in within it. But that's also another property that should be discussed. So to start off, we'll start off by talking about boron nitride nanoparticles. So there are several types of boron nanoparticles that have been developed. So boron nitride nanotubes, known as BNNT, boron nitride nanosheets, BNNS, and boron nitride nanoribbons, which is BNNR. Nanostructures based on hexagonal phase. So as you can see on the image on the right, they are a hexagonal structure. BN bonds are isoelectric, which means they have the same number of valence electrons with the carbon-carbon bonds. And they are very similar to carbon nanotubes. So kind of the difference between all of these types of nanoparticles is the nanotubes, as the name implies, is a tube. The sheets and the ribbons, the sheets kind of lay out like a big large piece of paper that spans in all sorts of directions, while the nanoribbons are more kind of linear and narrow. So these structures, there are several, so amorphous form, hexagonal form, cubic form, and wurtzite form. The amorphous form lacks long distance regularities. The hexagonal form, similar to the graphites in nature, they do have strong covalent bonds between boron and nitrogen. And then the cubic form, they're similar to the structure of diamond, but less stable than HBN, which is the hexagonal form. And then the wurtzite form, it is more of a rare compound. The boron and nitrogen are grouped into tetrahedral structures. So it's kind of a little bit more easier to see with the images on the right. So as you can see, the cubic form, it's more of a cubic structure, or the wurtzite form. There more has a tetrahedral structure, and the hexagonal form, they're in the hexagonal forms, but they're kind of like sheets that lay on top of each other, one right after the other. And then some properties of the boron nitride is that they possess extraordinary mechanical properties. So interestingly, the resistance to oxidation, the uniform band gap regardless of chirality, biological compatibility with various biomedical applications as well. And so synthesis of high quality and high purity BNNT, which is the nanotubes, are difficult to meet with demand for biomedical applications. So they are quite difficult to synthesize. That's why they're not regularly used within the biomedical community, because they are so difficult to synthesize. And you can kind of see the similarities between the carbon nanotubes and the boron nitride nanomaterials with the image on the right. So they do have very similar properties with the tubing as well as the sheets and then the ribbons as well. And then some synthesis. There are several ways to synthesize this. One method is the top-down method, the breaking of van der Waals forces between hexagonal layers, which separates between the two-dimensional sheets of HBN. There's two types of exfoliation. So the chemical exfoliation carries out in liquid solvents and sonication, which breaks the van der Waals forces, which allows molecules to expand the atomic layers. This method produces a higher yield in nature, so it's a little bit more preferred. And then the mechanical exfoliation, atomic sheets are physically pulled from each other by using adhesive tapes, like actual adhesive tapes, to peel off the graphene sheets. I have an image at the end of this that kind of illustrates it a little bit easier to. And then there's also another method called bottom-up method. So the chemical vapor deposition, which is a method used to construct high-quality nanoscale films. In this method, a substrate is exposed to a precursor which reacts with the surface of the water to produce the desired film. And so the physical vapor disposition, there's two types of it. There's one called sputtering, which is a solid target is bombarded with energetic particles, and so the film can be produced on a wafer facing the target. And then there's co-segregation, which is a source of boron and nitrogen is sandwiched between cobalt or nickel and silicon oxide, which grows HBN films on the metal surface. So here's the image that I was talking about earlier, where the top-down approach is on the left, bottom-up on the right. You can see the bulk sample of the top-down approach. You just enter in some energy, and then it produces a little bit of powder, which transforms to smaller fragments. This produces the exfoliation of multi-layers to monolayers, and then continuing the process, the nanoparticles are synthesized. Likewise, with the bottom-up approach, the precursor contains molecules. You ionize those molecules with energy, and then they produce the undesired molecules, but then you condense it and use the formation of clusters to create the clusters, which when duplicated creates these nanoparticles. So then the nanoparticles can be produced into fullerenes, diamonds, and graphene nanosheets, like the image kind of relays. And then some applications of boron nitride. So hexagonal boron nitride can act as a good lubricant in both high and low temperature systems. It can be used in ceramics as part of high temperature systems, so it is very resilient to high temperatures. Cubic boron nitride is widely used as an abrasive, which is kind of illustrated on the right. So you can see that the abrasive is being used to sharpen mechanical tools. And it can be used into tool bits and cutting tools. So amorphous boron nitride, layers of amorphous nitride can be used in semiconductor devices. So moving on to silicon nitride. So silicon nitride is an important nanoparticle in industry where it's used as a ceramic powder. Used because of its high strength, high fracture toughness, high thermal shock resistance, low coefficient of thermal expansion, and good wear resistance. So you can kind of notice a trend between these nitride nanoparticles as they are very tough in nature. And so there are a few different types of these silicon nitride nanoparticles. There's alpha, beta, and gamma silicon nitrides. So these alpha, beta can be synthesized under normal pressure, while the gamma nanoparticles need high pressure to be synthesized. And you can see on the image on the right, the alpha particles are trigonal in nature, while the beta are hexagonal in nature, and then the gamma are cubic in nature. So the trigonal and hexagonal, you can kind of see that they are a little bit similar, while the cubic are much larger. And then some properties of silicon nitride nanoparticles is the alpha phase has a higher hardness than the beta phase, and the alpha phase is more chemically unstable than the beta phase. So it's kind of a give and take. At high temperatures, when liquid is present, the beta phase is thermodynamically more favorable, and the alpha phase is converted into a beta phase. So the graph on your right is kind of a temperature versus tensile strength. You can see that 1997 we are able to produce much stronger silicon nitride nanoparticles because of the tensile strength is increasing, while back in 1980 it wasn't so strong. And then you can see at the bottom it says typical conventional ceramics, so you can see that it is much more beneficial to use silicon nitride than any other ceramics due to its just pure toughness. And you can also see whenever you increase the temperature, the tensile strength does begin to decrease rather exponentially. So synthesis of this, I apologize, the image cut off. So the material will be prepared by the heating of powder silicon between about 1300 Celsius and 1400 Celsius in a nitrogen environment. So it does need relatively high temperatures to be synthesized, which is kind of a downfall of it. And then there's the reaction there. And there are other silicon nitride phases, varying oxidation states, gaseous silicon mononitride, silicon mononitride, and silicon quesquinitride. And then some applications is because of its hardness, resistance to wear, and thermal stability, silicon nitride was first used for cutting tools. And then silicon nitride can be used as an insulator and a chemical barrier in electronics. And it can also be used in high temperature applications like ceramics, like I mentioned earlier, that can survive thermal shock gradients from rocket thrusters. So the image on the right is silicon nitride automobile bearings. So within an automobile engine and rocket thrusters, it can get to very high temperatures. So having a material that can withstand those temperatures is very important. And then moving on to gallium nitride. So this is a nanoparticle that is also very hard material and has very many uses and applications, probably more so than the previous two. It does have a Wurtzite crystal structure, has a wide band gap of 3.4 electrovolts, provided many applications to optoelectronic devices. It does have a low ionization radiation, making it a great material for solar cells and satellites. And then in addition, gallium nitride can make a great amplifier at microwave frequencies. So the image on your right is just kind of, it gives you an idea of the structure of gallium nitride. You can kind of see how complicated and interesting the structure can be. So properties of GaN, it is mechanically stable and has a wide band gap semiconducting material. It does have, very similar to the previous two, it does have a very high heat capacity, and it is thermally conductive. Gallium nitride can be doped with silicon or oxygen to form an N-type, or magnesium to form a P-type. So the result of this is that it does produce a brittle GaN crystal, so it's not particularly favored since we obviously don't want a brittle crystal. This contains field electron velocity calculated to be 1.9 times 10 to the 9th centimeters per second. And then just some information about the synthesis of gallium nitride. They are synthesized by the gallium particle trapping effect in a dinitrogen non-thermal plasma with metallic gallium vapor. So the synthesized particle size can be controlled by the amount of gallium vapor, which can be adjusted by plasma emission ratio of nitrogen and gallium. This was investigated through a high resolution transmission electron microscope, and then you can use the microscope to confirm the synthesis as well. And this kind of gives you a little bit more information about it. A recent study kind of did this experiments just to kind of prove that you are able to manipulate the sizes of the gallium nitride particles. So the scanning electron microscopy of images of synthesized nanoparticles at various gallium nitrogen emission ratios with nanoparticle size plots. So for this particular study, they did a 1:1 ratio, 1:1.6, and 1:2 ratio. And what they kind of proved is, as you can see that through the images in the graph on the right, is that that as the ratio increases, the diameter of the molecule decreases. So the 1:1 is they do produce relatively large size, and then as the synthesis ratios decrease, the particles get smaller and smaller. So some applications of gallium nitride. It is probably the most commonly used nitrides of the three. So it is based on violet laser diodes, which are used to read Blu-ray discs. Gallium nitride transistors are suitable for high frequency, high voltage, high temperature, and high efficiency applications. Utilized in military electronics such as array radars. And then gallium nitride nanotubes are utilized in nanoscale electronics and nanowires. So the image on your right is the blue laser diodes that are used to read Blu-ray discs. So you can see that they do have many applications as well. This is just a few of them. I couldn't list them all because there was quite a many, but even with the other two, they did have several applications with them, but this one is of course the most common. And then here's my works cited page. There were quite a few studies that I was able to find about these nanoparticles and a few Wikipedia information. One of the studies, let me just go back. This one in particular was very interesting to read just because it was discussing how the ratio between nitrogen and gallium was able to change due to the ratios like I mentioned earlier. So it was an interesting article, but other than that, that's basically it for this discussion. Thank you for watching.